Okay, so now it's time to do the calculations for this molar volume of hydrogen lab. There's going to be several steps, so just follow along. If you have a question, you can always email me or put it in the comments. And so I'm just going to jump right into it. Now, the first thing I want to do is to find the mass of the magnesium ribbon that I actually used. And remember, I measured out 100 centimeters of it. The length of my ribbon is 2.35 centimeters. So I'm just going to set up a little ratio where 1.589 grams was the entire 100 centimeters of magnesium, and that was for 100 centimeters. So I want to know what mass would be proportionally for only 2.35 centimeters that I used. All right. And when I do that calculation, I get point x equals 0.0373 grams of magnesium that I used. Okay, so you just have to get that. And a reminder that this is 3 significant digits, whereas my balance would have only given me 2 sig digs, so I'm feeling good about that. The next thing I want to do is to figure out the exact pressure of the hydrogen in my apparatus. Now, the barometric pressure was 770.8, but remember that that pressure is made up of two gases, the hydrogen and the water vapor that evaporated into the space. So what we're going to do is make use of Dalton's law, which says the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual gases, which is hydrogen and water. So let's put in the total here. So this is my correction factor. And that'll be equal to the pressure of hydrogen plus the pressure of water. Now, what is the vapor pressure of water? I went to a handbook, the CRC Handbook of Chemistry and Physics. It's awesome. And looked it up in the table of vapor pressures. At 19 degrees Celsius, which is where I'm at, water can be expected to add 16.477 torrs to the total pressure. As the water temperature would increase, more would evaporate, and so that vapor pressure would go up. So it is temperature specific. You'll have to just find a resource that will give you yours at your temperature. And if I subtract out the vapor pressure of water, the pressure of the actual hydrogen is actually 754.3 torr, not as much as the total where it matched the barometric pressure. So that's my correction factor. Okay, so pressure of the hydrogen, so let's put that in here, 4.3 torr. And next thing I'm going to do is I want to correct the volume to STP because that's our baseline, that's our standard. And what we're going to do then is use the combined gas law, or sometimes called the general gas law. Okay, and I know the volume of my gas at this pressure, so 754.3 is the pressure I want to use. The volume is 36.75 milliliters. I don't have to change that to liters right now. And then the temperature was 19 Celsius or 292.15 Kelvin. Make sure you're using Kelvin temperatures when you're doing these gas laws. Now, let's say this gas were to be adjusted to standard pressure, which is 760 torr, and standard temperature, which is 273.15 Kelvin. What would the new volume be at STP? So we do the math. It turns out to be 34.10 milliliters as opposed to 36.75 milliliters. So the volume would shrink a little bit as it went toward standard temperature and pressure. So correct it to STP, let's do 34.10 milliliters. All right, and we're getting close. We just have a couple more steps. One step would be to figure out, well, how many moles of hydrogen were actually in there. We didn't measure that directly, but we did measure the mass of magnesium. And so we have to do some fun little stoichiometry to find the moles of hydrogen. We refer back to the original equation. Whenever you do stoichiometry, you have to have a balanced chemical equation. The magnesium plus the hydrochloric acid, which was aqueous, that was solid. Let's do that for fun. Produce some aqueous magnesium chloride and some gaseous hydrogen. What's great about this is that it's all 1-to-1 ratios, well, except for that. 1-to-1. And so my mole ratio is going to be nice and easy. 0.0373 grams of magnesium was used. And whenever you do stoichiometry, the first thing you want to do is make sure you get to moles. So 24.305 grams from the periodic table. That'll get me moles. And then you have to do a mole ratio, which gives me 0.00154 moles of hydrogen. So by doing this calculation inside my burette, my eudiometer, I produced, to the best of my knowledge, that many moles of hydrogen. So we're almost there. We got one more step to go. And that step is to simply take the volume, let's say molar volume, equals the volume of the gas that I collected, 0.0341 liters. I changed that to liters right there. And that contained 0.00154 moles. So proportionally, if I were to create an entire mole of hydrogen under these conditions, what would its volume be? All right, and a quick tap of the calculator shows that the volume would end up being 22.2 liters per mole. All right, so slightly different than Avogadro's constant, which is 22.4 liters per mole at standard temperature and pressure. But I would say I'm pretty pleased with that. It's not bad. I'm pretty close. Maybe in your travels, your chemistry travels, you'll do better than me. But as long as you do your best and to carry through the calculations like this, 22.2 liters per mole. We'll put a little heart next to that because I think that's a pretty good result. Okay, so there you have it. The calculations for the molar volume of hydrogen lab. And if you have any questions, please email me or send me in the comments. In the meantime, happy experimenting and have a great day.